Good morning, everyone. It's 10 a.m. I see you are still joining. All right. Okay. That's recording. Right. Okay, well said. First of all, before we start, the current homework is due midnight today, right? That the previous one, the postponed one, which I postponed because of the problems about resistors and currents. Right? Okay, so what are we going to do today? In the previous class, which was yesterday, right? We practiced how to analyze a single resistor, right? One resistor, and basically, if you know three parameters, that circuit trinity, right? R, maybe I can write. So if you know R, resistance, current, and the potential difference, Ri delta V, you pretty much know everything about that resistor. And of course, every time when you analyze them, you need to also remember Ohm's law, which basically connects these three quantities, right? So we know how to analyze a single resistor, but quite often we see more than one resistor, right? So today we're going to look at that situation, those situations, but of course in special cases when resistors are connected either in parallel or in series. Of course, there are plenty of situations where none of these work, right? But those cases we will discuss later. Today, only when resistors connected in parallel, either in parallel or in series, right? Okay, so I prepared a few pictures to save some time, right? And so first, let's derive what we need, discuss physics what we need, because we did not have lecture, right? Because of the holiday, right? So I have to fill this up. And then we will start looking at the example, right? Okay, so now let's start sort of deriving and discussing physics. Again, the same idea of equivalent resistance is very similar to the idea of equivalent capacitor. Lots of similarities, right? Even derivation will be very similar, right? So let's assume that we have two resistors connected in parallel, right? And battery, delta V. And again, the whole idea, you just need to replace these two resistors with a single, okay, whatever number of resistors you have, with a single resistor, which we call R equivalent. And when you do this replacement, the rest of the circuit, in this case, it's just a battery, must work in exactly the same way. It's a very important sort of statement. So if battery provided delta V over here, exactly delta V must be here in the equivalent circuit. If current I was taken from the battery in the real circuit, exactly the same current must be taken in our equivalent circuit, right? Okay, and now remembering this, let's start discussing this. And again, it's just a bunch of resistors, so we have to analyze three parameters. So let's start looking. R, we want to get at the end, we want to get the formula which can be used to find R equivalent. So we will look at that later. So we have only these two parameters left, I and delta V. And first, which parameter out of those two is the same for these two resistors? I think now it should be obvious, right? Potential difference, because over here on this side, these points are the same potential, and these points at a different but the same potential. So as a result, potential difference exactly the same across the resistors and equals to the potential difference provided by the battery. So I can write potential difference across the battery equals to potential difference across the first resistor equals to the potential difference across the second resistor. And now I want to add one additional piece of information to this. Look, so delta V1 equals to delta V2 and equals to the potential difference provided by the battery. But since this battery must work in exactly the same way over here as well, so over here in the equivalent circuit, also we have delta V, which is equal to that and equals to those two. And also this delta V is just right across the this resistor R equivalent. So potential difference across R equivalent, of course, equals to this equals to that, and this equals to this and this. So it means that potential difference across an equivalent resistor equals to potential differences across resistors connected in parallel. We will use that piece of physics to analyze that problem, right? So now I can add that it's also equals to potential difference across an equivalent resistor. So let me frame this. Okay, maybe I will use green, right? So this piece of physics we will need. It's a first important piece of information. Now, okay, so we use delta V. R will be at the end. So now we just need to look at the current. And current, obvious, we have a junction point. So current I leaves the battery. Then there's a junction point. So of course this current will be split. I1 will go through this resistor, I1, and I2 will go through that resistor. So conservation of current, yesterday we discussed that. So I equals I1 plus I2. So I can write I, this current, equals to, you know what, let me step just slightly, move slightly lower. Right? I just need some space, right? Okay, let me write, so I use conservation of current. Conservation of current. Right, so I equals I1 plus I2, right? Right. Okay, so now we need to write this expression in terms of delta V, because they're the same, and the resistance using Ohm's law. Ohm's law, right? So I can write that this I1 equals to what? Ohm's law, let me write it over here in this way. R equals delta V over I, right? So I need to get I, so I, it will be delta V over R. So this is equal to delta V, right? And I drop the subscript because all delta V's are the same. So you see I have just delta V divided by R1. And this equals to, again, delta V divided by R2. Again, there's no subscript because all delta V's are the same. But in order to find the total current, every time we have to use an equivalent circuit. So let's get the total current, because again, total current here and total current over there are the same, because the rest of the circuit must work in exactly the same way. Okay, so from an equivalent circuit, I can write that I, again, using Ohm's law, it will be delta V across an equivalent resistor, right, which is still delta V, divided by R equivalent. So we can use this, right? So let me drag this. It goes into this side. So now let's just rewrite using these substitutions. And as a result, we will get finally basically the formula. So delta V over R equivalent equals to delta V over R1 plus delta V over R2. So you see delta V gets canceled. And as a result, we're getting the formula which we need to analyze resistors connected in parallel. So it will be 1 over R equivalent equals to 1 over R1 plus 1 over R2. Okay, so let me frame this in red. All right. So from this, we need to remember this important piece of physics to analyze, like we've done analyzing capacitors, and the formula which can be used to find equivalent resistance. Okay, and now let's do something similar for the resistors connected in series, right? And again, right, we replace two resistors with one in the rest of the circuit, in this case battery, but it can be more complicated than just battery, must work in exactly the same way. So delta V here, delta V there. If current I is taking from this battery, exactly the same current must be taking from the battery in our equivalent circuit, right? And again, three parameters, R, I, delta V. Again, R we will have to get at the end. So let's just leave it alone. So we have I and delta V. So which quantity, I or delta V, is the same for these two resistors? I think it's obvious. Since we don't have any junction points, current, conservation of current, gives us information that current over here in this resistor and current flowing through the second resistor must be the same. At this point, it's obvious, right? I don't have to convince you in that. We discussed it in the previous class, right? Okay, yesterday. Right, so I can write as a result this I equals to the current through the first resistor equals to the current through the second resistor. And now I need to add additional piece of information like I've done over here. Now, since this current is the same as here, and this current, which is total current, of course, flows through the equivalent resistor. So current through the equivalent resistor equals to this current, equals to that current, and equals to the currents flowing through resistors connected in series. Right, so over here I can write it also equal to I current through the equivalent resistor. Okay, let me frame it because we will need it to analyze circuits like that. Right, you see, here we needed this, we will need this and this, and now we will need this and the formula which I want to derive. And derivation will be very similar. But now, of course, we use current, so now I have to use delta V. And what can we say about delta V? Probably I use blue. So the total voltage drop across the whole circuit, this delta V, must be equal to delta V1 plus delta V2, right? So I can write, so the total delta V1 plus delta V2. Right, so let me write it over here. So, again, let me step a little bit lower. Delta V equals to delta V1 plus delta V2. Okay, my handwriting is getting worse, closer to the surface over there. Right, and again, using Ohm's law, now Ohm's law which connects all these three parameters, quantities. So we need to get delta V1. Delta V1 will be R1 times I. Currents are the same, so I'm not going to use subscript next to currents. Right, so this is R1I, this is R2 times I. And in order to write this, the total potential difference, right, we will use the equivalent circuit. This delta V equals R equivalent times I. Right, so let me write it over here. So delta V equals R equivalent times I. So I will take this and plug it over here. Even the structure of derivation is very similar to the structure of a derivation which I used to discuss capacitors. Here, very, very similar. Right, so now once you replace these delta V's with these RI's, we will get the, basically we will get the formula. So R equivalent times I equals R1I plus R2I. Again, no subscript next to current because I use immediately this fact. Right, so currents can be cancelled and we're getting the formula. And we are ready to start analyzing that problem. Right. Let me somehow manage to write it here. R equivalent equals to R1 plus R2. And of course, if you have more than two resistors, just keep adding. Right. Let me frame it. Right. So this piece of physics and this formula, that's what we need. Again, remember, so if equivalent resistor are placed resistors connected in series, then current here and currents there must be the same. If resistors were in parallel, then potential difference across an equivalent resistor equals to the potential difference across resistors connected in parallel. Okay, so that's what we need. And let me check if I mentioned everything. Yeah. And now let's look at the example. Again, I prepared picture in advance so that it would look better and save maybe a couple of minutes. So we have battery, delta V is given 3 volts. Okay, maybe I should step away from what I just wrote, right? It's better to be on this side, right? So potential difference provided by the battery is given, and then resistors are given 3 of them. And I picked nice numbers. R1 has 1 ohm, R2 has 2 ohms resistance, and R3 has 3. It's easy to remember, right? Nice numbers. Right? And so we need to analyze this circuit. What does it mean, analyzing circuit? Okay, about battery, once you know the potential difference, you know everything. And we have 3 resistors. And again, whenever you discuss resistors, you need to know Ri delta V. Resistances are given, so it means that we need to know current through each of the resistors and potential difference across each of the resistors. So that's what I wrote. So we need to analyze. It means I1, 2, 3, currents through each resistor, and delta V, 1, 2, 3, potential differences across each resistors, right? Very similar idea of the solution. Idea is very similar to the idea which we used analyzing capacitors connected in series and parallel. So first, we need to simplify the circuit to the simplest possible, to something like this, right? And then we will start moving back using these pieces of physics as bridges to find everything that needs to be found. But first, we will simplify using these formulas which we just derived. Right? Okay. Again, guys, if something needs more time, if something needs to be clarified, okay, just say something. Right? So first, let's start with simplification. Again, I will draw my pictures from top to bottom, right? And then I will write something on the right, and then I will write on the left, moving back. So first, let me use green. So which two resistors connected either in series or in parallel? Right. If none of the resistors are connected, if a resistor is not connected neither in parallel nor in series, then of course this method is not applicable. It will be just illegal, right? It will be criminals from the mathematical point of view. Right. Okay, so these guys obviously are connected in parallel because potential difference between across this resistor and this resistor will be exactly the same. It doesn't matter how we drive this circuit. Potentials at these points are the same. Potential at these points are different but the same, and of course, as a result, potential difference is going to be the same. So these are. Let me write. Where should I write it? Parallel. Okay, let me just write underneath. So parallel, right? And so for simplification, right? So instead of this circuit, I can draw something like this. Again. Battery must work in exactly the same way, right? And now instead of these two resistors, I will introduce an equivalent resistor, and I will label it as R12. Makes sense, notation, right? We replaced resistor R1 and R2, so I use notation R12, right? And R3 is still there because we don't do anything with that resistor, right? And battery still works in exactly the same way. Again, still the same delta V. And if current I is taking from this battery, exactly the same current must be taken from the battery in this equivalent circuit, right? Okay, so now let's find R12. So parallel case. So we need to use these reciprocals. Okay, I don't like this formula, but no options, right? So let me probably I will write underneath. So 1 over R12 equals 1 over R1 plus 1 over R2. Okay, we can start immediately calculating, but I usually bring to the common denominator, flip it. So it will be R12 equals to R1 times R2 divided by this sum of R1 and R2. So as a result, R12 will be equal 1 times 2 divided by 1 plus 2. So it will be 2 over 3, right? 2 over 3 ohms. All right, let me check. Yeah, 2 over 3 ohms. Right. Okay, let me circle it a little bit because I will need it when we start moving back. Okay, so that's the first step. Okay, let me put some lines separating. So now we need to move deeper, right? These now two resistors obviously connected in series, right? Okay, this corner, it doesn't do anything, right? So R3 and R12 are in series. Okay, let me write over here. Connected in series, so as a result, we can simplify and create the simplest possible circuit, right? So it will be battery which works still in the same way, then an equivalent resistor, which now I will label it as R equivalent because it's a final, so I can call it, yeah, the ultimate equivalent resistor. And battery is still the same delta V because the whole method was developed like this, so we don't want to disturb the rest of the circuit. And again, the same current will be taken, of course we don't know this current for now, but we know that current over here, here, and there will be the same. Okay, and now of course let's find the R equivalent. Case series case, we need to add resistances, R1 plus, but in this case R3 and R1 too, right? So, so now I can write, so R equivalent equals to R3 plus R1 2, right? So far no objections, I hope, right? Okay, so now we can plug numbers. R3, it's a 3 ohms plus 3 ohms plus 2 over 3. Right. So if you bring to the common denominator, it will be 9 over 3 plus 2 over 3. It's 11 over 3. 11 over 3. Okay, ohms, but running out of space, so I'm not going to write units. Or maybe I can squeeze it. Ohms. Right. Okay, so now, look at this circuit. We know the value of the resistor. We know the potential difference is still the same 3 volts. Now we can find the total current. And that's the advantage. That's why we simplified this circuit so that we can find the total current. Because if I asked you from the very beginning about the value of the current, you wouldn't be able to tell me. Unless you are very experienced and you can do this quickly in your head. Right? So that's why we simplify the circuit, so now we can find the total current. So we can find at least something about our circuit. Like I told you, right, when we analyze capacitor. So we need to just create a crack in the wall. And that's the creating that crack. So we can find something, and now we can expand that crack and see the whole truth, right? Okay, so now we can find current, total current. Right. Okay, I will separate that. And now total current. And of course, that's the total current to the equivalent resistor, right? So I equals, so delta V divided by R equivalent. So which is 3 divided by R equivalent, 11 over 3. 3 divided by 11 over 3. So 3 goes upstairs. This 3, you will get 9, 9, 11. 9 over 11, right? And of course, units of amp. So that's the total current. That's the crack, right, in the wall. Now, knowing that, we can start moving back, revealing the truth. Right. And moving back, we have to use, of course, these bridges. Information about either the same current or the same potential differences. Okay, now I will use maybe red. Right, so now this, moving from this circuit to that circuit. And these are equivalent. Replace 2 resistors connected in series. So what is the same between R equivalent and resistors connected in series? Series, this case, currents. So it means, and we know this total current, I, right? So, which flows also through R equivalent. So this current will be equal to the current through that and that. So let me write that bridge. Okay, I'm trying to estimate the amount. Let me move slightly lower. Right, so I equals to I3 equals to I12 equals to 9, 11 amps. Right, so that's the bridge. Right, okay, I maybe separate, right? So that's our bridge, which we need to use to move from this circuit to that circuit. And now look, we know the value of resistor R3, 3 ohms. We, from the bridge, know the current flowing through the resistor R3. If you know current and resistance, you should be able to find delta V. Now we have to use Ohm's law, that law which connects all these 3 parameters, Ri delta V. All right? So now we can get everything that we need about the resistor R3. Okay? So now I can write, so we need to get now delta V3. Delta V3 equals to R3, okay, R3 times I3. And as I said, current comes from the bridge, which is 911. R3 is 3. All right. You know what? I will write underneath. 3 ohms times, okay, 911. 9 over 11, right? Okay, amps. Let me write also amps. 2711, really? Looks so ugly. Yeah, 2711 volts. So now, we know everything about resistor R3. We finished analyzing resistor R3. We know its current, we know its potential difference across. And the value of the resistor R3 was given from the very beginning. So we finished analyzing R3. But it's not the whole story. We still have plenty of information inside of R12. So now let's first define the potential difference across R12 in a similar way. And then we'll move to the next step. Use the next bridge. Right, so delta V12, because now we know current through that resistor. We know the value of R12. We can find the potential difference. Piece of cake. So R12 times I12. And I12 comes from the bridge, as I said. Right? So R12, 2 over 3. 2 over 3 ohms times 911 amps. So 9 can be cancelled, so we'll have over here 3 times 2, 6 11th. Volts. Right. Okay. So now we exhausted the first step. Now we need to make the next step from this circuit to that circuit, because as I said, instead of R12, we have plenty of information. So now we have to move over there, right, using the fact that inside of R12, there are 2 resistors connected in parallel. So as a result, we can write the bridge, parallel case, potential differences in equivalent resistor, and potential differences across resistors connected in parallel must be the same. So we need to use this bridge. Right. So now let me write it at the top, that bridge. So it means that delta V12, which we just found, you see everything is well connected. Delta V12, it's at this 6/11, must be equal, according to this bridge, equals to delta V1 and delta V2 in equals to 6/11. 6/11 volts. You know, let me erase that current because it's overlapping. Let me show that current over here. Right. Okay. So now we have the bridge, and now we're using that bridge and Ohm's law, we can find currents through R1 and R2. So let's start with R2. So we know the value of R2. We know potential difference across R2. Finding current, delta V divided by R. Trivial, right? So I2 equals delta V2 divided by R2. Delta V2, again, it's from the bridge, 6/11. Volts divided by R2, 2 ohms. So 6 and 2 get cancelled. We have 3 upstairs, and in the denominator 11. So 3 11s, right? Yeah. 3 over 11 amps. So that's the current in the second resistor. And so now the last one in exactly the same way. So I1 equals delta V1 divided, delta V1 divided by R1. And again, delta V1 from the bridge. And R1 was given from the very beginning. So it's a 6/11 divided by 1 ohm. So this is volts, this is ohms. So we will get just 6 over 11 amps. Done. You see, structure is very, very similar. Idea is very, very similar to structures and ideas we used analyzing capacitors. Right. So now I can write done. Right. Make sense? Again, so first you need to simplify the circuit the simplest possible. And again, every time students don't have troubles getting to this point and this, but very often this part messy on the exam when students are in the classroom, right, and not at home, right. So, okay, it should be enough, right? So you got the idea, and then now the rest is just a practice. Now I need to erase something, and I feel like erasing still that part, if you don't mind. Okay, if you're not screaming, then I'll start erasing. Cool. Right. So it's like a silent agreement. Although I feel like keeping it. Okay. I will try to redraw it for the next class. So now, actually it's a chapter 28, not 27. It's a chapter 28, looks like. Why I thought it's 27. Okay, so the next problem is, the previous, it wasn't from the book. I just made it up, right? That's why the numbers were so nice. So now problem 16. Very similar will be in your homework. So what do we have here? 3 resistors are given. The values of 2 are known. The values of the 1 is not known. All right, so let me draw something. 1, 2, 3. So let's say this is R1 10 ohms. This is R2 15 ohms, and R3 is not known. I know, label was erased. Then, but it's not the whole story. What else we know? We know that current flowing through this structure, I, is 100 milliamps. Then, it's not the whole story. We know that the potential difference across the whole structure, delta V is, I think, 5 volts. Yeah, 5 volts. So that's what is given. We need to find R3. Okay, so what can be done here? Okay, I used to ask, right, so for suggestions, right, but then I decided to create sort of like a, not create, draw, or write everything which is relevant to this problem. Of course, relevant from the physics point of view, right? And again, we have a bunch of resistors, right? So every time we had to play with these 3 parameters, Ri delta V and the formula connecting them, right? So let's write everything that we can about Ri delta V, and then by looking at that, we should be able to identify all possible solutions. Let's do that, right? So let me write, so 3 parameters. So I R delta V, right? So let's write everything that we can. Which one I discuss first? Okay, current. Okay, let's do with current. Let's start with current. So I. So what do we know about the current? Current, since there are no junction points, previous class, conservation of current with no junction point, current is the same. I1 equals I2 equals to I3. So that's what we can get about current. Right, so I can write I1 equals to I2 equals to I3. And of course equals to I, 100 milliamps, right, given. Then, and so basically this doesn't give us an equation. All right, it gives us a very important piece of information, but in order to find R3, we need an equation, which can be solved using maybe this in order to find R3. So it's important, but not enough. So now let's look at what next. Delta V. Let's look at delta V. Potential differences, right? So what can we say? Obviously, delta V1 plus delta V2 plus delta V3 must be equal to the total potential difference across the whole structure, right? So delta V equals to delta V1 plus delta V2 plus delta V3. Okay, cool. Now we have an equation which can be used probably to solve the to find R3. But we still have R. What can we get about R? R, not much. We can try to use equivalent resistance, method of an equivalent resistance. Okay, let's add that as an additional option, right? So in this case, resistors connected in series. So we can use this. Sorry. So R equivalent equals to R1 plus R2 plus R3. Okay, cool. This gives us actually an equation, which can be also used to find R3. Okay, so we exhausted everything that what we can get about these 3 parameters, but of course every time we also need to use a formula which connects them all, right? And formula connecting them. And of course, formula connecting them, right? So, which is Ohm's law? Okay, formula connecting them, these 3 parameters. So, which is, okay, let me write this way. So, the way it's written, R equals delta V over I. So, that's all we can write about this problem. So now let's think which method we can create. Again, as I said, in order to find R3, first of all, we need to have an equation, right? How many equations we have? We have this equation and that. This is, yeah, we can use it every time, right? And of course, this is the important piece of information, which of course we will need it, but the solution will be first method will be structured based on this formula about delta V's. So the first solution will be, let me use this green. So if we use this piece of physics and the formula connecting them also, this will be method number 1. Based on this equation, of course, important piece of information we will have to use. And of course, every time we need to use the formula connecting these 3 parameters. So the first method will be. The second method will be based on this formula. So the second method, I'm invading this part and I don't like this. The second method will be based on this. Of course, this piece of physics and of course, the formula connecting. So this will be method number 2. So now let's use method number 1 and then method number 2. Okay, now I will put number 1 in circle. Method number 1, which is based on that. Okay, so let me rewrite that formula. So delta V equals to delta V1 plus delta V2 plus delta V3. And so now we can use this formula connecting them all, 3 parameters, and we can replace this delta V. So R1I, currents are the same, right? Currents are the same. I can over here write also it is equal to I, which is given, right? So this delta V, total delta V is given 5 volts, right? So I can write it R1 times I plus R2 times I plus R3 times I. Again, you see, I dropped immediately subscripts next to current because I used this fact, right? Important piece, just to save time and space, right? So now, again, current is given. So let me take this current, I can factor it out and bring it to this side. Delta V over I will be equal to those resistors. Delta V over I equals to R1 plus R2 plus R3. Basically what? Everything is given except for R3. Given, unknown. One equation, one unknown, so problem is almost done, right? So from here, I can write that R3 will be equal to delta V over I minus R1 and minus R2. Plug numbers, and it's done. Delta V 5 divided by, okay, maybe I can write. So R3, 5 divided by 0.1 amps. 100 milliamps, it's 0.1 amp, right? Then minus 10 and minus 15. Minus 10, minus 15 ohms. So this will be 50. Minus 10, minus 15, so it's a 25. 25 ohms. So that's method number 1, but we still have method number 2, which is based on equivalent resistance, right? And right, of course, what we have now, this solution should be based on this formula. So R equivalent equals to R1 plus R2 plus R3. How many unknowns do we have in this equation? R3 is unknown. R equivalent, we also don't know. So 2 unknowns, one equation doesn't sound good, right? So this is our final goal. So it means that in order to find this, we need to somehow find R equivalent. And so far, every time in order to find R equivalent, we use that formula in what I just erased, right, in that example. But now we don't know this, so we cannot use this formula to find R equivalent. So how else can we find R equivalent, not using this formula? How else can we use that? How else can we find R equivalent? And we can do this. Look, this is our circuit, right? Original circuit. I can redraw and I can draw an equivalent circuit. You know what? Let me add also Okay, it will be too much of overlapping, but sorry, I have lack of space, so I have to do it. So I can, for example, imagine, of course it's not given in the problem, but I can easily imagine that over here and draw that somewhere over here there is a battery, right? Which provides this potential difference, 5 volts, and drives this current 100 milliamps. It's basically this case. Let me draw this circuit, equivalent circuit, right, over here. So, of course, I can draw my R equivalent and that imaginary battery which created that potential difference, right, and that current. And you remember when we replace real circuit with an equivalent circuit, battery works in the same way. So it means that if in the real circuit delta V is 5 volts provided by the battery, in the equivalent exactly the same. So I can write over here, so it's a delta V equals 5 volts. And current must be the same. So if this current of 100 milliamps is taken from the battery, exactly the same current must be taken from the battery in the equivalent circuit. You remember all these discussions. So exactly the same current I of 100 milliamps is taken from the battery in the equivalent circuit. And this delta V is across an equivalent resistor, and this current flows through the equivalent resistor. Can we use this circuit to find the value of an equivalent resistor? Piece of cake. Again, Ohm's law. We know the potential difference across the resistor. We know current. Okay, so now let me write from the equivalent circuit. From the equivalent, I abbreviate equivalent circuit, we can write so R equivalent equals to delta V divided by I. And if you plug it over here, you will get exactly the same equation like over here. Right, so I can plug it, and as a result, I will have delta V over I equals to R1 plus R2 plus R3, which is the same as here. So now from here, you can solve it in exactly the same way, right? Okay, let me write, which is the same. Okay, let me show the same to what? Right. The same to what we had in the previous method, right? So now, of course, you can solve it for R3 easily, right? Because now everything is given for except for R3. So you will get 25 ohms in a very similar way. In your homework, you are going to, I think I don't remember if I assigned this problem again, just for practice. I don't remember it. I thought about, sometimes I do that. But definitely you have I think problem 17, or no, 23, I think, which idea is very similar, but your resistors are not going to be connected in series. They're going to be connected in parallel, right? But idea is the same. You can write, for example, these, right, all pieces of information, right? And one of the solutions will be based on the fact that current entering into the whole structure will be equal to I1 plus I2 plus I3. So that will be one solution based on that. Or you can use an equivalent resistor, again, like what we've done here. And again, equivalent resistor can be found using the equivalent circuit, right? So it's an idea, philosophy of that problem will be very similar, but of course you'll have to use different formulas, right? Okay, so that's, of course, I plan to discuss, okay, one more problem, but I had doubts that I will be able to get to this problem. Okay, we'll see. All right, maybe I will, but I like discussing that problem, which maybe I will discuss it next class, which will be on Monday, right? Okay, I will think. Okay, it should be enough for you to do your homework. So tomorrow in the lecture we will start discussing Kirchhoff rules. Okay, so if you have questions, go ahead. Otherwise, I will see you tomorrow in the lecture.